Okay, so we'll continue our discussion of the construction details here. So in the last class we have discussed about salient type. Okay, we have discussed the two types of rotors here. One is cylindrical type rotor, the other one is salient type rotor. Cylindrical type rotor, the other one is salient type rotor. In the salient type rotor, we have discussed that there are projected poles like what we have seen here. Here I would like to add one point, that is damper bars here. Damper bars and importance of damper bars. Okay, damper bars, what are these damper bars here? These are the bars, okay, which are placed under the this pole shoe. Okay, these are placed under the pole shoe. So it's like a copper bar. These are the bars. Okay, if you want to represent in 3-dimensional here, these bars will be placed like this. Okay, these bars will be placed like this. Okay, these bars will be placed, same projected poles will be there here, these bars will be placed like this. And there is some why we place some components in the machines unless it has some importance. Similarly here also in the machines, in the salient type rotor, we place damper bars purposely or intentionally, because here damper bars is used to prevent hunting. A small sentence has been written, but the explanation for this required is very it takes 10 to 15 minutes. Okay, it prevents hunting. So what is hunting? I'll try to give a just generalized overview here. Hunting is nothing but, okay, there might be suppose let me try to give a generalized example. That is, let's assume that two bikes are moving with some 50 kilometers per hour. Both bikes are okay, moving with 50 kilometers from one point. Let it from one starting point here. Okay, both are rotating at same speed. Okay, now moving with same speed. Now here, let's assume that suddenly there is a path hole, a pit. Okay, some disturbance or some speed breaker is there for only for bike A. Now what has to be done here? Now will the speed remain same? He or she has to reduce the speed from 50 kilometers hours to 40 or 30, whatever it is. But whereas what happens to the B? There is no disturbance here, so that he will continue to go with the same speed here. Now here, after the disturbance, again what happens here? He will continue with the same 50 kilometers per hour here on. Now here, whatever the speed loss, whatever the loss that has been done here, okay, is it going to be recovered here? Now previously both are starting from same point. Both are starting from same point. Now will that be same case now here? If I assume at this point here, now if the B person is there here, then definitely A person will be lagging. Am I correct or wrong? Yes or no? Okay, last. Okay, now A person will be lagging with respect to B here, because there was a disturbance that occurred to the A person, who is moving with 50 kilometers per hour here. So due to this here, though now even though he is moving with a speed of 50 kilometers per hour, still he cannot be on par or in the same position, okay, or stationary with respect to the B person, because there was a disturbance occurred here. And I can say that similarly, instead of, I hope you understood this example. Now let's try to correlate the same example with respect to this machines here. Now I'll consider the B person as rotating magnetic field. B person as rotating magnetic field. What is this rotating magnetic field here? RMF, rotating magnetic field, which rotates at what speed? Always at synchronous speed. I hope everyone knows it. Rotating magnetic field always rotates at synchronous speeds here. Next here, what about the A person? A person is nothing but rotor speed. Rotor speed here. As a heading is synchronous machine, it always has to rotate at what speed? Synchronous speed. Whatever the 50 kilometers per hour I am assuming here, it is actually rotating at synchronous speeds here. But due to some mechanical disturbance, okay, due to some mechanical disturbance or electrical disturbance or due to some disturbance, okay, the rotor suddenly pulls back. Okay, rotor suddenly pulls back for some instant. Okay, I am just explaining you in generalized. Okay, now here after the disturbance here, again it is overcoming the disturbance. Again the rotor starts rotating at same synchronous speeds. But due to that disturbance, whatever the 1 second or 2 seconds that this disturbance time here, so rotor is not in par with in same position with respect to the RMF, rotating magnetic field here. Now, though the rotor is now rotating at 1500 RPM here, it is not the initial position. Okay, it is not in the same as the initial position with respect to the stator. Okay, it is not the same as the initial position with respect to the stator, and we call this concept as hunting. Okay, rotor is always trying to catch the stator flux. Okay, rotor is always trying to catch the stator flux. Okay, but it is unable to do because of there was a mechanical disturbance that occurred here. So I can add something to this. Okay, now at starting I'm just generalizing the things so that you can able to understand in a better way. Okay, so due to some mechanical disturbance, if the rotor which is previously rotating at synchronous speed, now what is actually happening here? Okay, the disturbance occurred, and again though rotor starts rotating at synchronous speed, it is not in the previous position like before the disturbance here. Okay, so if both parts are rotating or moving at same speed here, so what I can say that what is the relation between these two parts or two bikes here? It is stationary with respect to each other, because both are rotating at what speed? Same speed. Okay, but there is a disturbance occurred. If disturbance is occurred from the both ends, then again also both will be rotating at stationary. Okay, now both are rotating at same speed and it is stationary with respect to each other. But what is happening here? Disturbance is occurring to the only one part, that is only onto the rotor. That's why it is always trying to catch the stator RMF here, and that concept is called as hunting. Hunting is nothing but chasing. Hunting is nothing but chasing. So that's why they have named down this as hunting here. We'll try to discuss in detail in the synchronous motors and other things also. So as of now, what is hunting here? Nothing but due to some mechanical or some disturbance, the rotor pulls back and it is unable to rotate at synchronous speed. Once after the disturbance, though the rotor starts rotating at synchronous speed also, it is not in the initial position with respect to the stator. Okay, let's assume that if the stator I am giving notations as some position 0 degrees or 10 degrees or 30 degrees. Okay, so previously whatever the A pole that is there, that is with respect to 0 degrees. Now it is not the same here. It may be lagging with respect to some 10 degrees or 15 degrees. Okay, that disturbance is called as hunting here. Okay, that disturbance is called as hunting, and we can also extend in such a way that rotor poles and stator poles will be magnetically aligned. Okay, wherever magnetic flux is there, can I assume that virtual poles are formed or not? Yes or no? So even I can assume that in the stator side also there are poles are there. So stator poles will align magnetically locked with respect to rotor poles here. Okay, but due to this disturbance here, what is happening? There is slightly disturbance here. I can say that. So I can also add like this. Just I am generalizing these things so that you can understand in a better way. This is stator pole. This is rotor pole. So previously both are exactly magnetically locked, but due to this hunting, what is happening here? Slightly rotor will be, okay, this is stator poles and this is rotor poles here. If it is rotating in clockwise, now here is it the same position? It is slightly behind. Rotor pole is slightly behind the stator pole. Both are rotating at what speed? 1500. If two buses are moving in the same 4-line road, in the 2-line road, if I assume that both buses are moving with a speed of 80 kilometers per hour. Normally we see in our BVRT while going from college to Nasabur. Okay, we can see that. So when two buses are moving with same speed here, will be constant, stationary with respect to the other bus. Okay, the same happens, but due to this disturbance here, whatever the magnetically locked that concept is there, so it is slightly shifted here. Because of that, the same 100% magnetic locking is not existing, and it may lead to some other problems here. So this is what is hunting. Okay, this is what is the concept is hunting. We can explain the same concept in other matters also. Okay, now here to prevent hunting, what I am doing here, damper bars. Okay, damper bars here. To prevent hunting, we are using damper bars here. So I can add two concepts here. I can say that damper bars, or I can also say that damper winding. Damper bars or damper winding. Okay, damper bars or damper windings here. So I can consider the two possibilities here. I will consider in the two possibilities. One is below NS, below synchronous speeds. Okay, below synchronous speed. Let's assume that for a 4-pole machine, if the synchronous speed is 1500 rpm, so if the rotor speed is decreased, okay, if the rotor is rotating at some 1490 rpm or whatever it is, okay, the rotor is rotating at 1490 rpm, okay, though the machine is rotating at 1500 rpm, it is just slightly pulled back, okay, slightly pulled back here. Now here, what is happening here? due to some mechanical disturbance, the rotor is rotating at less than the synchronous speed. Now what we'll do here, this damper bars will comes into picture. So I can conclude that this damper bars will comes into picture. Now what is required here in order to make this, in order to shift this position, in order to increase the speeds, what we require here? We require some mechanical energy. Yes or no? I need to move this duster from here to there. For this reason, what I require here? Mechanical energy. If I want to throw this duster to the last point, I need more mechanical energy, more energy. So similarly, if I want to increase the speed here, what I require here? I require more mechanical energy. Output is more mechanical energy is there. So I need a device which can able to convert the output as mechanical energy. Is there any machine? Machine. Input is electrical energy and output is mechanical energy. Now here what happens here? This extra mechanical energy required, this extra mechanical energy required by the machine will be given by damper bars. Now the damper bars will act as a motor. Now the damper bars will act as a motor. What the purpose of motor here? Which will convert electrical energy into mechanical energy. It will convert electrical energy into mechanical energy. Again, motor to generate force, energy, what we require here, current carrying conductor, magnetic field, and third one is relative motion. All the three conditions are satisfying or not? All the three conditions are satisfying, so that now the motor, this damper bars will be acting as a motor, and once the machine, so that this extra energy is given to the rotor, so that the rotor will comes into the correct position. The rotor is correctly magnetically locked with the stator, which is previously it used to be, okay, before the disturbance. Okay, now what this damper bar is doing? It identifies that what is the fault and what is the rotor speed. When the rotor speed is less, what it understands that it requires more mechanical energy, it requires additional mechanical energy, so that this damper bars now behave as a motor which converts electrical energy into mechanical energy, and it supplies additional energy to this rotor, so that now the speed has been increased to 1500 rpm. This is how it will try to reduce the external disturbances. This is what actually happens when the rotor rotates less than the synchronous speed. I hope it is understood, and I guess there is no need to dictate the points. Okay, I can conclude that when the rotor rotates at less than the synchronous speed due to some external disturbance, it's normally not happens in synchronous machine, but due to some external disturbance, the damper bars acts as a motor which converts electrical energy into mechanical energy and provides the energy to the rotor, so that the rotor will be brought to its original position, similar to that of before the disturbance. Okay, before the disturbance. This is what the concept of damper bar. This is the function of damper bars below the synchronous speeds. Okay, below the synchronous speed. Coming to the above NS, only synchronous machine rotates only at synchronous speed. It will never be rotating at below the speed or above the speed. Okay, we discussed the possibility due to some external disturbance, if it is rotating at below the speed, what actually happens. Now we are also seeing that what actually happens if the rotor rotates above the synchronous speeds. Okay, due to some external disturbance. Suppose that the voltage is increased or whatever it is, the input has been increased, so that the motor starts rotating more than that. Okay, the frequency increase or whatever the possibilities are. Okay, due to some disturbance, that's why I am generalizing that. Due to some disturbance, okay, if the rotor starts rotating at above the synchronous speed, is it also acceptable for synchronous machine? Yes or no? It's not acceptable. Again, what happens here? Damper bars comes into picture whenever there is a disturbance is occurring here. So it's like a protector. It's like a savior to the machine. Okay, is someone is waking up this damper bars? No, it is doing automatically. It is coming into picture automatically. Whenever there is a disturbance, it automatically identifies. Now the speed is what is happening here? Now the speed is greater than the synchronous speeds due to the disturbance. Okay, this occurs only in some problem here. Okay, speed is greater than the synchronous speed. Now here, when the fan is rotating at more speed, what does it mean here? It has more mechanical energy. Am I correct or wrong? It has what is the correct word? It has more mechanical energy. It has more mechanical energy. Okay, whatever the more mechanical or excess more, or I can say that excess, this excess mechanical energy which is making the rotor to rotate at above the synchronous speed, I want to convert this into electrical energy. For this, what are the component that I am using here? Again, I am using the damper bars. Now, damper bars is acting like a which device? Is there any device which converts mechanical energy into electrical energy? Generator. Yes. So, the damper bars now acts as a generator which converts mechanical energy into electrical energy. Is it converting all the mechanical energy into electrical energy? No. It is only converting the excess mechanical energy into the electrical energy. It is converting the excess mechanical energy into the electrical energy, and that's the purpose of damper bars here. So there are three possibilities. One is rotating below the speeds. When the machine is rotating below the speeds, okay, how the damper bars are behaving here? You will expect an objective question. So when the rotor is rotating below the synchronous speed due to disturbance, damper bars acts like a motor which converts excess electrical energy into mechanical energy. When the machine is rotating as above the rated speeds, then damper bars acts as a generator which converts excess mechanical energy into the electrical energy. Okay, when the rotor is rotating at synchronous speeds, then is there any work for the damper bars? Okay, I guess not. So when everything is going on well, is there any need? So there is no need here. So when everything is going on well, so when the rotor is rotating at synchronous speed and it's magnetically locked with respect to stator poles, so then there is no purpose, there is no significance of damper bars. You can also expect one more question here. When the rotor rotating at synchronous speeds, damper bars function is insignificant. Okay, it is not useful. It is not insignificant. It won't be useful for any purpose. Okay, it is insignificant. It will be inactive. It will be in inactive mode. What are the appropriate word? You can use it here. This is the conclusion of damper bars here. So I didn't explain this because the explanation required for this, so that I just kept aside here. So this is the conclusion of damper bars here. Okay. So damper bars, the one word he has given, that it prevents hunting. So we have discussed what is hunting. Okay. What are the methods to reduce hunting? Okay. Methods to reduce the hunting, and that we discussed in synchronous motors. Okay. Now here, how damper bars will be helpful in reducing the hunting here. That is, if it is below the rated speed and above the rated speeds, how the machine behaves. This is the most important competitive exam objective bits. Okay. You will not write unless you understand the whole concept. Shall I proceed? Okay. You just keep writing in the running notes. So we have already given enough time. Okay. Okay, now we will try to discuss EMF equation of alternator. Okay, EMF equation of alternator. So it is similar to that of transformer EMF equation. Okay, so just simultaneously quickly write down here. Let's phi equal to flux per pole. So what are the additional things that are there? Okay, well, I'll try to discuss that. Okay, phi equal to flux per pole. P equal to number of poles. Okay, Ns is synchronous speed. If you already know, then there is no need to write. Okay, Ns is synchronous speed. Z equal to total number of conductors. Okay, conductors or coil side, both are same. Yes or no? Conductor or coil side, we have discussed in detail in the previous classes. Conductor or coil side here. Okay. Number of conductors equal to 2 times thrice that of the turns. T is nothing but number of turns. If 10 turns are there, how many conductors are there? 10 into 2, that is 20. Have you discussed the single turn coil or multi-turn coil? Yes or no? A coil can be single turn or multi-turn. Okay. T phase is nothing but turns per phase. Okay, so here you can see this here Z phase. How many phases we have here? R phase, Y phase and B phase. We have 3 phases here. If I want to consider in terms of phase, okay, I have to divide it by 3 here. Okay, and here in the turns per phase, what they have given here, so T equal to Z equal to 2T. Z equal to 2T. Just now I told you that if we have 10 turns, how many conductors are there? 10 into 2, 20 conductors. So T equal to Z by 2. What is Z here? Total number of conductors. So number of turns equal to total number of conductors by 2 here. If I want to consider per phase, then here T per phase equal to Z by 2 into how many phases we have? 3. Okay. How many phases we have? Z by 2 into 3 here. Okay, Z by 2 into 3. Okay, next here we can be single layer or double layer. Single layer winding or double layer winding. What does it mean here? Single layer winding or double layer winding? Single layer winding is nothing but if in a slot, if only one winding is placed, then that's a single layer winding. Whereas double layer winding is nothing but, we have discussed everything in all this in the DC machines, in the windings, armature windings concept. Try to revise if you are not familiar with this again. Okay, so double layer winding is nothing but in a slot, if I place 2 conductors to generate more EMF, okay, I can place in a slot I can place 1 winding or two windings or 4 windings also. Okay, that is multi-layer winding. Okay, so if I place if I place more number of conductors in a slot here, that is the multi-layer winding. Okay, single layer winding or multi-layer winding here. As I am placing 2 conductors here, that is a double layer winding here. Okay, so as per that, how many conductors per slot? This is depending upon what is the concept. Either it's a single layer winding or double layer winding or triple layer winding. Okay, same room is there. Okay, machine is designed with the same space, but I want to generate double the energy, double the voltage or double the power. So here, without changing all the dimensions here, just if I can accommodate, instead of placing a single conductor in a slot, if I can accommodate 2 conductors in a single slot, then EMF equal to 5ZNP by 60A, the basic equation. Okay, that is DC machines here. Okay, so phi is proportional, E is proportional to Z. So EMF induced will be double. Okay, so wherever we increase the number of conductors, the EMF induced will be increases. It is twice. So this is what the concept of this number of slots into number of conductors by 2 by 3. Why I am discussing all this in detail? Because you have to use these concepts in the numericals. That's why I am stating clearly. Okay, so nothing new is there. Whatever I have written, if you can read right, that will be more than sufficient here. So now what is total number of conductors? If total number of conductors are 500, then how many turns will be there? 500 by 2. 250. Let's assume that it is 480. Then total number of turns will be 480 by 2. That is 240. Then next, total number of turns per phase. Total number of turns per phase. That means how many phases we have? R phase, Y phase and B phase. So 240 by, again I have to divide it by 3. So 240 by 3. What is the answer? 8. So 500 is the total number of conductors. T, 240 is the total number of turns. T phase, 80 is the turns per phase. 80 is the turns per phase. So you have to use the corresponding term in the equation. That's it. Okay, you are not doing anything new here. Just we are converting the formula or term as per our requirement here. Here we need to discuss this additional thing here, pitch factor and distribution factor. We'll have to discuss in detail. Just keep these terms aside for some time. Okay, there are 2 terms will be there. Kp is pitch factor, Kd is nothing but distribution factors. We'll discuss in detail. There are separate terms are there. You can ignore these terms here. Just initially Kp and Kd will be included in the formula. That's it. Same, whatever we discussed in the EMF equation, okay, in the previous EMF equation, everything will be similar to that of EMF equation. So that whatever the transformer is formula equation is there, same concept is there. Only thing just where I'm including Kp and Kd. Okay. So here, if average EMF induced is equal to, that is flux cut per by time taken here. That is EMF is proportional to, always we already know that D is proportional to d phi by dt. As we are already discussed so many times here, just I'm going on quickly here, so you can rewrite later also. Okay, just you can leave some space and you can write it later if you are unable to catch. Okay, so E is proportional to d phi by dt, and how this flux depends upon it. The change in flux depends upon number of poles here. If it is a 4-pole machine, so it is that will be affected 4 times. Okay, so d phi will be phi and time change will be 60 by ns here. We already discussed this. So equation will be 5 pn by 60 here, and if I simplify this, we can say get that average EMF per phase equal to 2f phi z. Phi is flux, z is nothing but number of conductors here. We know that z equal to 2t. Okay, so the equation will be changed. Average EMF equal will be changed to 4f pi f t. Let's try to write on here 4 pi f t here. We are just familiar with this 4.444. Okay, 4 pi f t here. Now we already know this. There is a formula called form factor, peak factor and form factor. Peak factor equal to RMS. Okay, that's maximum value by RMS value. Okay, average value, and form factor equal to RMS by average value. So here you might be seeing this 11.1 kV, 33.3 kV, 132 kV. Only if you see any substitutions here, the voltage will be specified to the particular ratings only. It's because of this form factor. It's because of the form factor. The form factor of AC sinusoidal waveform is 1.11. Okay, it is 1.11. Just to satisfy this value, so you can see that the generated voltage will be 11 kV, 132 kV, 33 kV. Okay, or else if you want to step down or step up, it will be in this manner only, because it has to satisfy the form factor. It has to satisfy the form factor. Okay, so we want to converse always AC supply is always considered in RMS. Always AC supply is considered in terms of RMS, whereas DC maximum value is equal to RMS value equal to peak value equal to, in DC only there is only one value. Yes or no? If you see the waveform, this only single value will be there. Whereas for in AC, if I consider this total waveform, in AC maximum value is different, RMS value is different, average value is different, and we can still all these values are different. So always AC supply we will consider in terms of what? We'll consider in terms of RMS. Come on. We'll consider in terms of RMS. Okay. So always AC supply RMS values will be, okay, AC supply will be in terms of RMS. Okay. Always we'll consider AC 230 volts. Is that what is the value here? That is RMS value. 230 volts will be always RMS value. They will specify that by default. If I specify that 230 volts AC, that is RMS. What is that RMS value? VRMS equal to Vm by root 2. So can I able to calculate maximum value? V maximum equal to root 2 into VRMS. Try to understand here. Okay. Always we will try to represent the AC values in RMS only. Why I am discussing? Because just I am interrelating the other things also. Okay. So 230 volts and everything is in RMS. Okay. Now here for form factor, what is the form factor of AC supply? 1.11. The form factor is 1.11. So from this I want to calculate RMS value. What is this value here? Is this average value or not? This is average value. So we already know average value and already I know form factor. Can I able to calculate the RMS value? So I'm doing the same here. So RMS value equal to so that is RMS value equal to 1.11 into average value. 1.11 into average value. Okay. 1.11 into average value. Okay. So here what happens here? So what actually happens here? This 1.1 into 4 ft, 4 pi ft. So it will be converted into 4.44 pi ft. Is it not? Is it the similar equation that we already followed in transformers or not? Okay. But only thing is here we are including two terms here: pitch factor and distribution factor. In this, we are type of winding that we use here. Okay. There are two different types of windings that we use here. As per the different types of windings here, when a differently placed windings, will there be effect on the EMF or not? Definitely there will be effect on the EMF. So as per that, it is affecting. There are two factors will be there. One is pitch factor, other one is distribution factor. So pitch factor is Kp and distribution factor is Kd. So the final equation will be, this is the final equation, 4.44 Kp Kd pi ft. Okay, just quickly write down this in 2 minutes. What are the time that it takes?